this is my first time doing a virtual seminar as well, so it could be a little bit of a learning curve. So yeah, today I'll talk about my work since I started in June 2017. So it's all to do with continuous optimization, convex optimization. Jonathan Eckstein, of course, is an expert in that field. So we've been working on this algorithm called projective splitting. It's basically an algorithm for solving convex optimization problems, and it's got a lot of really nice features. It's not as famous as some of its cousins like ADMM, Fister, and other operator splitting methods, but I think it has a lot of neat, nice advantages. So let's get started. So projective splitting is this method. You can use it for solving convex optimization problems. When I started working on it in 2017, it had one or two disadvantages, big problems that I noticed and Jonathan and I worked on. The first big issue that the method had was that it didn't have a way of using gradient calculations. So if you're doing basic smooth optimization, you have a smooth function. The most obvious thing to do is to compute gradients, so derivatives, and then take kind of derivative negative gradient steps or something like that. And the method was actually based on something called the proximal operator. We use these proximal calculations, which in a lot of cases is much harder to do than to compute gradients. So the first thing that I worked on was trying to figure out ways that you could use gradient type calculations within the framework of projective splitting. And so that's primarily what I'll talk to you about today. I also did some work on deriving convergence rates as well, but I won't have time to talk about that today. So yeah, so basically today I'm just going to give you the rundown of how projective splitting works and also explain how this new gradient step version works. And yeah, as Wahid said, feel free to ask any questions by whichever channel works best. So feel free to interrupt me. Okay. I just thought I'd start off by talking about the problem scope of projective splitting, because I've just said that it's a method for solving convex optimization, but actually in its most general form, you can use it to solve monotone inclusions. And this is basically what happens when you take the derivative of a convex function. You end up with a monotone operator, and finding the zeros of the derivative is solving a monotone inclusion. And so that's one. Convex optimization is just one special case, but you can also solve saddle point problems and other things as monotone inclusion. So I just mentioned that to say that projective splitting can be applied to a wider range of problems than just optimization. Although we basically only focus on convex optimization so far. I think we probably should be looking into saddle point problems, because that's something that has received a lot of attention, at least in machine learning, but that's probably something to do in the future. Okay, so what optimization problems are we interested in? So this is typically called composite optimization. What we mean by composite is when you have an objective function that is the sum of two terms. So this is our objective we're trying to minimize. It's f1 of c plus f2 of c. Now, this is just, in the simplest case, we have Euclidean space, so this is just a d-dimensional vector that we're minimizing over. And this comes up a lot in kind of model fitting problems, machine learning. You might have one function that's fitting the model to whatever the data set is, like a loss function, and then a second function that is kind of playing the role of a regularizer. So it's there to promote the sort of structure that you're after in the model. So maybe that's a low rank model or a sparse model or something else. So it's really kind of, you're doing a multi-objective type problem where you're trying to get a good fit for the model, but you're also looking for something which has some particular structure, like sparsity being the most famous example. And this comes up a lot in compressed sensing type problems for 2 decades or so now. Machine learning type problems, they end up having a similar flavor of optimization, even though the goal might be slightly different in those two applications. One you're recovering an object from measurements, and the other you're doing something like fitting a model to a data set, and the regularizer might play a different role, but the optimization ends up being fairly similar. And my interest in this is in designing algorithms, so we wonder what are good algorithms for these sorts of problems. And to answer that question, let's look at what are the challenges in the modern era. So there are lots of different challenges. The most pressing, I guess, most people know is that we just have more and more data to deal with. So that is a blessing and a curse in the sense that you can train better models and bigger models and more complicated models. But from a computational point of view, you then have to worry about that. You have to worry about dealing with bigger data sets, bigger models. You have to do more computation. You also have to worry about things like memory, and that's actually often the real bottleneck is in pressure on the memory system. So these are the sorts of things you have to think about when designing these algorithms. Other challenges that are on our minds when we design these algorithms, this one's more to do with the actual optimization problem, and that is that there'll normally be some kind of non-smoothness, non-differentiability in the problem. So we have this function that's the sum of two, the objective is the sum of two functions. Regularizer is chosen to be some non-smooth function, like L1 norm, Euclidean norm, total variation norm. Okay, and this is because we now have 1 or 2 decades of experience in seeing that these choices are the ones that work well to promote the structures that we're after. And so L1 being used for sparse when you want a sparse solution, Euclidean norm when you want a low rank solution, and so forth. And so, why is that a problem? So if you're familiar with convex optimization, you know that you can compute subgradients usually of these sorts of functions, and then you could perhaps use the subgradient method. But in practice, that doesn't work very well, just doing a kind of vanilla subgradient approach. You have to pick some step size, which decays to 0 at the right speed. Convergence rate tends to be quite slow, just of a basic subgradient method. So there's this advent and growing interest in proximal methods, proximal operators, which is another way to deal with non-smoothness. And they tend to perform a lot better using this thing called the proximal operator, which I'll explain in a couple of slides. And that tends to work a lot better. It tends to have faster convergence, and also ultimately it's also better at getting the actual structure. So if you're looking for a sparse solution, using proximal type methods will actually get you a sparse solution, typically. And then there are other approaches which also can deal with non-smoothness, like Frank-Wolf methods as well, which I won't talk about today. Okay, so what are these first proximal methods, first order proximal methods? First off, by first order, I just mean that it only uses the gradient of the smooth function. So we're not computing Hessians, we're not computing second order information, and that's a good thing, because most of the time computing a Hessian, that's a big matrix. Maybe you have to invert it. They could be high computational and memory complexity. So we want to avoid doing that. Of course, there's a trade-off, because second order methods converge a lot faster. There's some sort of trade-off depending on what the application is, whether you want to use a second order method. And then there are also quasi-Newton methods which work pretty well. But basically, we've had over the past 10 or so years a real rise in interest in these first order proximal methods, so that they're really have performed quite well in certain applications. Now, projective splitting, the method I've been working on with Jonathan, will fit into this class of methods. Okay, so that's what we're talking about today. Let's continue. So yeah, projective splitting is one of these. It fits into this class. So I wanted to explain a bit how it fits in with the other more famous cousins within this field of proximal methods. So let's do a bit of background on first order proximal type methods. So let's start off with a simpler optimization problem. So here we're minimizing just a single function, which is convex, and now we have a constraint set C. So we have a set C, which is closed and convex, and the goal is to minimize f on this set C. So within this family of first order methods, what you can do is do something like this in the box, which is you iterate by computing a gradient of the function and then taking a negative gradient descent type step. You have to pick this scalar step size row in the right way. And then after you've computed that might no longer be a feasible point. So this might end up outside. This is the set C here, this kind of circular thing. When you compute the gradient, you might go outside of the set. So what do you do then? You project the result back onto the set C. And so that will now be, this is the Euclidean projection, the closest point in the set C. And you iterate this way, and this will converge to a solution of this function, of this optimization problem. That's nice. But remember, the problem we were interested in is this pink one. We have a sum over two functions. Okay, so how do we solve this type of problem? So in order to solve this type of problem, we need to introduce the proximal operator. And this is actually a mapping from one vector to another vector. So it takes an input as a vector and outputs another vector. It's really the solution of a subproblem, another optimization problem. So let's just assume F1 is smooth, F2, we don't know if it's smooth, it could be. And we're actually going to compute a minimizer of this optimization problem. It's F2 of Z plus a quadratic regularizing term. And if you do this, this is the proximal gradient method now. You do essentially the same thing as projected gradient. You do a negative gradient descent step, but now you compute the proximal operator of the input. And this works. This will converge to a solution of the pink problem. And the reason it works, to get some intuition, if you haven't seen the proximal operators, it's basically generalizing projection. If I were to pick this function F2 to be this here, which is really an indicator of the set C, so it's 0 on the set C and then plus infinity everywhere else, then the proximal operator is just the projection onto the set C. So the proximal operator inherits all the properties of projection. It really generalizes projection. So that's nice. So this is a very kind of fundamental method. It's, you may wonder about this. I have to solve this subproblem at each iteration, so that could be a problem. It could be complicated, but there are many cases where this has a closed form solution. Oh, I got a question here. Let me see if I can find the chat. Is there a condition on F2? Yeah. No, the only theoretical condition is that it's a convex set, technically convex, closed, and proper, for this to be a well-defined subproblem. But the other implicit condition is that you can actually compute this, because we're not saying anything about how hard it is to compute this actual subproblem. Now, in practice, there are lots of examples where you can do that. The L1 norm is the canonical example where you can just compute it in a closed form. But actually, a big motivation of the work I've been doing with Jonathan is to try to extend projective splitting, that method, to cases where you can't compute this in an easy way. Okay, so let's continue. So that's the proximal gradient method. Now, what happens if I have, instead of just a single regularizer, I have many regularizers? So this is the situation where, okay, we still have one function, which is kind of a loss function, a data fitting term. But let's just say I wanted more than one structure. I didn't just want sparsity. I also want low rank. I also want something else, low total variation norm. Who knows? It depends on the application. But you could easily imagine situations where there's lots of different things you might want. For example, in sparse group lasso, that comes up in image recovery, that can come up there. How do we deal with this? Now, for the proximal gradient method, this becomes a problem because this proximal operator you now have to compute it as with a sum of functions inside this subproblem. And that's, even if each one on its own has a nice prox, even if I can compute it easily for F2, once I start adding terms here, it might not have a closed form anymore. Okay, so this is a more complicated problem, we have to do something a little bit more sophisticated to solve these sorts of problems. Okay, so let's look at this more complicated problem in the box. Instead of having a sum of 2 functions, we now have a sum of n functions, which we're minimizing. So how can we solve these sorts of problems? Well, today I'm going to give you a new method that can solve it. Projective splitting itself is not new. It goes back 12 years since Jonathan and Bernard Spider, they first wrote a paper on projective splitting, but original form couldn't handle this type of problem. So that's yeah. So we've got a new way to solve it. There are a few different ways to solve it that I'll also discuss, kind of competitors. But let's give you kind of the nutshell definition of projective splitting in a nutshell. The basic idea of projective splitting, the reason it's called projective and splitting, well, let's explain this. So we were trying to minimize the sum of functions. Let the solution set of the optimization problem be this blue set. So this is the set of minimizers. You may have just one minimizer, but in general, for convex non-smooth problems, you might have more than one minimizer. The basic idea is that you have some current estimate of the solution, create a hyperplane that separates this estimate from the solution set. This is going to be the green line here. If you can construct such a separating hyperplane, then you can always make progress by projecting onto that hyperplane to get the next point. And then just rinse and repeat. So do the same thing, construct another separating hyperplane and project onto that. Construct another separating hyperplane and project onto that. And then you continually, over and over again, until convergence, sort of in the limit, you will converge to a solution point. Okay, so that sounds great, but the reason this actually works in practice is that there is a procedure for constructing these hyperplanes. So there's a procedure that uses the proximal operator of each individual function in this sum to construct this separating hyperplane. And that's why it's called splitting. Splitting meaning that you've got a sum of functions, but you can deal with each function individually. Okay, and yeah, that's the kind of intuition of the method, which is not too hard to explain, although the details can get kind of messy. And yeah, in terms of what I'm talking about today, previously this method worked just by using proximal operators of each function, but it had no way of incorporating gradient information. So if any of these functions was differentiable, there was no way to use the gradient. That's really what I've been working on, and I'll tell you about today. I guess I have time to just talk about some of the other approaches, some of the other methods out there. There are other ways you can solve this problem within the first order proximal family. So it would be a mistake to not mention ADMM, which is, easily the most famous method I'll mention today. Jonathan has a paper on ADMM with Stephen Boyd. It has like 15,000 citations and counting. It's very popular and very effective. It's a little different to projective splitting and some of these other methods in that you have to minimize the augment and Lagrangian at each iteration, and that is in principle it could be a difficult calculation, although in practice there's usually some structure that makes that an okay calculation. So it kind of relies on slightly stronger assumptions that you can compute this minimize the augmented Lagrangian rather than just computing proxies and gradients. But it's very popular and very effective. So there's ADMM. There's also a few other methods that are quite similar to projective splitting. There's 3-operator splitting, Chambol and Pock style, Primal-Dual splitting. Much more recently, there's this forward-reflected backward style method. So these are also very interesting. So these 3 methods all use very similar assumptions to projective splitting. They're kind of the bare bones assumptions on the problem. They're also typically the analysis for these sorts of methods is based on a fixed point analysis. The idea there is that you're basically to get from one iterate to the next, you're applying the same mapping. This mapping could be very complicated, like in the case of ADMM or any of these methods, it's very complicated, but it's always the same thing that you're doing at each iteration. And if you do that, and if this mapping is well behaved, like it's non-expansive, for example, then you will converge to a fixed point of the mapping. And then again, the fixed points of these mappings the mappings are kind of designed so that their fixed points solve the optimization problem. And that's just putting it into, I guess, a condensed form, but in reality, proving all these things is often very difficult. But that's typically how these things go. Now, why do I mention that? So the reason I mentioned fixed point methods is just that projective splitting doesn't really fit into a fixed point analysis. It's not really doing a fixed point iteration. Because at each iteration, we just have to construct a good enough separating hyperplane. And we don't have to use the exact same procedure to get that. We can use one procedure or another as long as it gives us a separating hyperplane. It has to ultimately be a good separating hyperplane that actually cuts deep enough towards the solution set. But it doesn't matter what procedure we use. You can use one procedure and then change it and then do something else. So there's some flexibility inherent in the analysis there that you don't get with fixed point methods. But with fixed point methods, if you want to do something different, I mean, at least I've seen typically people do that by adding some perturbation term, and then you have to control the size of the perturbation and make sure it goes to zero and stuff. So you can get some flexibility, but it's not exactly the same philosophy there. So some of the advantages of this flexibility in projective splitting is you get some properties, I would argue, fairly easily. Now, I might be biased because I've read all the projective splitting papers, so I understand them well, but I feel like it's, I'm familiar with some of the fixed point analysis approaches as well, and I just think that it's easier to get these within projective splitting. So what can you get? You can get incrementalness. Now that means that you have this sum of n functions, but you might not want to process every function at every iteration. This sum is huge, like 1 million functions. You don't want to do that. And that works pretty easily in projective splitting. So you don't have to process all the functions. You can end up processing a very small number of functions. Actually, I'll show you today one way you can just process a single function, as long as you pick it intelligently. So something similar to how stochastic gradient descent works in machine learning. You just have to basically process one function at a time. The difference is we're not picking it at random. We're picking it in an intelligent way. Okay, so that's incrementalness. Another thing you get is asynchrony. So a lot of these methods can be computed in parallel. I mean, you can do parallel computation. It's a little harder to get asynchronous parallel computation. So usually all the processes have to be synchronized so that you're really doing the same thing as a centralized algorithm, but just sending out information and getting it back at the same time. So projective splitting, you can do things somewhat asynchronously. It turns out if you do these calculations but slightly out of sync, you still get separating hyperplanes. A couple of other nice things, the step sizes can all change. You can use preconditioning. A lot of things are pretty easy to get, which are arguably more difficult in fixed point methods. So you don't have to process each function the same number of times. You can actually process one function many more times than any other function if that's more convenient. This is quite difficult to get in the fixed point methods, I would say. Although it might be possible, I'm not sure. Okay, so that's nice. So this, basically I've done a good job of selling you the previous model of projective splitting. But I wanted to also, because a lot of these advantages, they existed before I started working on it. But also, I wanted to say that I want to try to sell you the new model of the car as well. And that's what we've been doing since 2017. And that's how to incorporate gradient steps. So basically the method was using this prox calculation. What I was trying to figure out is how can we get it doing something like this, where it's actually just computing a gradient and then using that gradient. And so let's just hammer home the point of why that's a good idea. The proximal calculation is okay for certain types of functions like L1 norm, but in other examples, it's not as easy. So I just have here a quadratic function. This is a matrix A, AX minus B, and you're taking the L2 norm squared. So it's a quadratic. If you plug fx in here and try to solve this, you end up solving a linear system. Okay, so this is a linear system that you have to solve at each iteration. And that might be fine. There are lots of examples of matrices where that's fine. If this matrix has some kind of structure, it can be diagonalized easily, or maybe you can pre-compute at the beginning of the algorithm, just pre-compute this inverse, something like that. Then there are ways that you can do this, but as a general thing, this is going to have like n cubed complexity with an n by n matrix. it'd be nice to at least have the option of computing the gradient, because in that case, you're just doing 2 matrix multiplies. And yeah, so that's what we've been working on. And the good news is that we did solve that problem. We figured out ways that you can do that, where you can use gradients instead of the proximal operator. Basic idea is if you have any function, hold on, let me just read the question. What about the case when the function is yes. If the function's non-smooth, then you have to use the proximal operator. Yeah, that's the assumption here is if the function's smooth, okay, has a Lipschitz continuous gradient, then we can use the new gradient procedure. Okay, so the actual procedure we came up with needs to do 2 gradient steps per iteration. There's a much later, about a year after we came up with this, we figured out how to get that down to 1 gradient step. There's actually there's 2 versions we have now, and you don't have to. There's also a backtracking version, so you don't need to know the Lipschitz constant. And yeah. I did also work on convergence rates, but I won't have time to talk about that today. All right, this is where things get a bit messy. So let's go under the hood and try to explain how projective splitting works. So we're doing this, this is the optimization problem. Now you can convert that to essentially finding the zeros of the gradient. So this is a little confusing because some of these functions might be non-smooth, so we have to think about sub-differentials, not necessarily just gradients. But essentially, if all the functions were smooth, we'd just be looking for a point z such that the derivative is 0. Because some of the functions are non-smooth, we have to use the sub-differential. The sub-differential is a set-valued operator. So you input a vector and you get back a subset of vectors. And it's essentially going to be all the, let's just look at an example. So if you're not familiar with sub-differentials, this black function is non-differentiable at the point 0. The sub-differential is the set of all tangents, lower tangents. So it's really a range of possible vectors. And the optimality condition is just that 0 is included in that set. So this point is minimized at 0 function, and so that's because you can find 0 within the set of all possible sub-differentials at that point. So if f is differentiable, then the sub-differential just reduces to the regular gradient. Okay, so really projective splitting is aimed at solving this pink problem. This is actually called a monotone inclusion because subgradient or sub-differential is actually a monotone operator, which means it satisfies this property. So if I take 2 inputs, x and y, and look at the inner product between x minus y and the outputs for u and v subgradients, then that's always positive. This is what's called a monotone inclusion problem. Okay. So with the sub-differential defined, let me just say something else about the proximal operator. So if you take the derivative of this and set it to 0, then computing the proximal operator is really equivalent to finding a pair of vectors x and y such that x plus rho y equals a. So a is the input vector, and y is a subgradient of f of x. So this in the box is what we use as the kind of definition of the prox, at least in operator splitting. And it's a unique point just because this is a strongly convex minimization here. Okay, so let me try to explain the solution set here. So I was talking about this blue, if you recall, we have this blue set, this we call the solution set. What I'd lied about, or at least I hid under the rug, is that this is actually the Primal-Dual Solution Set. It's a set of primal solutions and dual solutions. So this is a convex optimization problem. So it has a dual and a primal form. And so let's define the dual or at least the Primal-Dual Solution Set. So we have to introduce W1 through Wn-1. These are dual vectors. And the definition of the solution is just, can we find a point, so a collection of z and wi, such that each wi is a subgradient of fi of z, and additionally this sum is 0. And so this looks really unnecessarily complicated because it's essentially just rewriting this condition here. We're just naming the subgradients, or at least the first n-1 subgradients. And so basically, if you found a point z that satisfies this, then it will also be in this set as well. We're just naming the kind of subgradients. It'll make our lives a bit easier if we introduce one more dual variable, wn. So this is going to be just equal to the negative sum of all the other dual variables. And then our condition is just that each wi is a subgradient of f(i)z. So this is, I think it's equivalent to KKT duality. It's just that we're writing everything in terms of the monotone inclusion. So it's a little different to how you might have seen it in elsewhere. But essentially, yeah, these wi's are the dual variables. Okay, so this is the definition of S. This is the solution set, and this is what we're looking to find. Is a point Z such that this condition holds. Okay, so how do we construct the separating hyperplane? We really want three things to hold. Okay, so we're going to parameterize this hyperplane via a function phi k. The hyperplane is going to be the set of zeros of phi k. So in order for this to be a hyperplane, we need phi k to be affine. Okay, so we're going to try to get these three properties. We need phi k to be affine. We want the solution set to be on one side of the hyperplane. And then we want the current estimate pk to be on the other side. So just by convention, we pick negative side to be this side and the positive side to be this side. So we want the solution set to be over here on the negative side and the current point pk to be on the positive side. So I'm going to show you how you construct this function phi k. And this is the definition. This goes way back to 2008, the original paper by Eckstein and Slider. And essentially all papers in projective splitting have used something like this. So this is the definition. So it's going to be a sum I equals 1 through n through all of our functions. And these are inner products, so dot products. And we introduced constants which define the hyperplane essentially. Xik and yik are just constants. You have to pick them at each iteration. And well, depending on what you pick for xik, yik, you get a different separating hyperplane. So they're really the parameters for this green line. As we vary x and y, we get different lines. So a couple of observations. First is that this is an affine function, ik. Now that looks confusing because you have z times wi occurring all over the place. But the way that we define wn cancels out everything. So this wn is the negative sum of the wi, so that essentially cancels out all of these products. So this is an affine function. Okay, now we have to choose, we want to choose this function so that the solution set is on the negative side. So any p star, this is any solution, evaluates on the negative side of phi k. It is negative, I guess. So the way that we do this is we pick each yik to be a subgradient of fi xik, and then we can use the monotonicity of the subgradient because we know that the solution set, each wi star is a subgradient of fiz star. So now this is really using the monotonicity property. Okay, so this is going to say that these are positive, and then, I mean, rather inconveniently, we pick the solution set to be on the negative side. I think if we could go back in time, I would tell them to do it the opposite way. But if you have a negative sign times a bunch of positive terms, this is going to be on the negative side. So this solution set's on the negative side of the, completely on the negative side of the hyperplane. Phew. Okay, so that's number one and number two. We've covered. Now we're left with number three. We need to pick the hyperplane in such a way that pk is on the positive side. So how do we do that? So we could ultimately we have to get there by choosing this pair of numbers xik, yik in some way. That's how we parameterize everything. Now we're constrained that yik has to be a subgradient, but we have some freedom in the choice of x. What we're going to do is we can essentially solve each of these n problems separately. We're going to just make each inner product positive. We're going to solve each one as a separate problem for I equals 1 through n. So let's look at that. So we want to find make each of these separate dot products positive. Let me just ignore the subscript and the subscripts for a second. So let me let x equal xik and so on. The actual math problem we're trying to solve is to pick a pair of vectors x, y, so that y is a subgradient and this inner product is positive. How do we do this? Well, this is where you can use the prox, and this was how it was done in 2008 and in the previous versions of projective splitting. You do a single prox calculation. The input is a vector, it's z plus rho w. If I rearrange this, I can use that alternative way of writing the prox as finding a pair of numbers, x plus rho y equal to the input, and y being a subgradient. And this works. I mean, you can see the algebra here in a couple of lines. If I take this expression and just rearrange it, I move w to the other side, I move x to the other side, then I just plug that into the inner product. And this, the inner product of the vector with itself is the norm squared. But this whole thing is positive. The norm squared has to be positive. So the prox is nice because you get two things for the price of one. You get a subgradient, and you also get that this inner product is positive. Okay, so yeah, that was kind of how it was done for many years. We thought, how can we do this with a gradient evaluation? So let's suppose the function doesn't have a nice prox that you can compute, at least compute easily. But let's suppose that the gradient is Lipschitz continuous to make it a fair game. So we want to update x and y in such a way that this inner product is positive. So we know that y is fixed. Y basically has to be a gradient of f, the gradient of f of x. It's unique now because this is just a Lipschitz continuous mapping. But we still have freedom in how we pick x. So this took some scratching on paper. Eventually we came up with this update. The idea is that you now compute a gradient at z, gradient f of z. And then you do something that looks suspiciously like gradient descent. It's not exactly the same because there's a dual variable. And that's how you get x. And then once you're done with x, you then do another gradient calculation to get y. There's really two gradient steps or gradient calculations here. Now, why does that work? Well, let's see if I can go through this quickly. So you basically can prove that this works using Cauchy-Schwarz followed by Lipschitz continuous the gradient. And you'll get that this inner product is positive. You get essentially the same bound we had before, but now you have rho inverse minus L times the same term from before. So there is an extra condition that you need to pick the step size rho less than 1 on L. And that's kind of what you'd expect. If you're doing gradient steps, you can't expect to be using huge, unlimited size step sizes. So you have to have rho less than 1 on L. So that's the basic idea. And when you put everything together, you get that each of these inner products is positive. So the sum is positive. And so the current point pk is now on the positive side of the hyperplane. For each of the functions in the sum, you either use a prox update or you can use the new gradient step update if it's smooth. And that's, that you might wonder, is that really enough to prove convergence? Yeah, there's a lot more work you have to do because, one thing you can imagine could go wrong is that these hyperplanes might not give you any separation. I could just pick the same hyperplane over and over again. It would, maybe stall the algorithm if that happens. So it turns out that this is a big enough gap. So when I prove that pk is pi k pk is bigger than this turns out to be enough to prove convergence, but without going into all the details. Yeah, so that's the basic idea there. Let's go through some basic extensions. So one thing here is that we need to know this Lipschitz constant. In this you have this two gradient step, you have to know the Lipschitz constant to set the step size. Now in practice, you don't need to know it because you can do backtracking. So you can basically just try a bunch of step size and check to see if you get if you get this condition here. basically whether your inner product is sufficiently positive. And if it's not, then you can just reduce the step size and try again. And if you do that, then within a logarithmic number of trials, you'll get to a good step size. That's nice. It's probably a good time to just go through the pseudocode and show how the whole thing works. So we have an optimization problem. This is our algorithm produces a primal point zk and then a bunch of dual variables as well. And the goal at each iteration is to make this a good separating hyperplane. Now this phi-kp parameterizes the hyperplane. So what you do is you go through and update each xik, yik. So this is for each I equals 1 through n, you can update it based on if it's smooth, you can do the new gradient step calculation. Otherwise, you do the original prox calculation. Then once you get all these xik, yiks, you then project onto the hyperplane to get the next point. And this projection is not the problem, not really a problem. The projection is I have a fly buzzing around my the projection is not usually a problem because it's just you compute the function phi k, that's some inner products and a sum. You have to compute some sums of vectors. So most of the actual computation goes on in computing these gradients or potentially computing the proxies. Let's see how much time. 250 already. Okay. So I think I'll probably skip that. Well, I guess, yeah, one thing I'll just mention is that you can do these calculations in parallel. So the way I've written it is as a for loop, I equals 1 through n. But of course, these can all be done in parallel. You can do this one at the same time you're doing this, a different I, and so on. So there's a very nice way to do things in parallel. Now, this projection has to be done, it's kind of a bottleneck because you have to coordinate everything in the projection. But if you look at what's actually going on, there's kind of sums of vectors and really these can be done efficiently using reduction type operations. So if you have a distributed system, you can do these in kind of relatively efficiently, the actual projection. Probably won't have time to talk about that. Another nice thing, so these things can be done in parallel. They can also be done asynchronously. And what I mean by asynchronous is that the inputs to these calculations can be slightly old. They can be out of date. So you can have different iterations. It doesn't have to be k here. It can be dik, which is just some iterate less than or equal to k. And projective splitting, the sort of theory allows you to get away with some staleness in the inputs there. So that's kind of a nice feature. We haven't actually implemented this in parallel yet. I'm working on that right now, but at least in theory, that's a great benefit to have. Another nice thing about that is that the step size constraint remains 1 on L. It doesn't get worse. If you have more asynchrony, you don't have to make up for that by using a smaller step size. Maybe I will have it. So I will actually discuss this. I think I have time. So the idea, what I mentioned to you earlier, is that you don't need to update every single function. So we have this sum of functions. You would normally process every single function at each iteration, but you can get away with just processing a small number of them. And let me show you how you can get away with just processing one. So the idea is that when you project pk onto the hyperplane, that means that pk plus 1 must satisfy this condition that phi k of pk plus 1 equals 0. That's what it means to be on this hyperplane. Now this sum is going to be equal to 0, which means it's going to have some positive terms and some negative terms. It turns out they can't all be 0. If they're all 0, you actually have found an optimal point. This is, without going into the details, that's actually an optimality condition. So in general, there's going to be some positive terms and some negative terms in this sum. Now the idea is you just pick one of the negative ones, because when you update it with either a prox or a gradient calculation, this whole thing flips to being positive. So if you have the sum equal to 0, and then I take one of the negative terms, make it positive, and keep everything else the same, then now the whole thing is positive. The whole sum would become positive. So you found a separating hyperplane. You just updated one of these pairs. Okay, so that's the idea. We call it greedy because in practice, what we do is we just pick the most negative term and update that one, even though that might not get the best separating hyperplane, because we don't know ultimately how much above 0 it's going to get after we process it. So it's kind of greedy heuristic. Okay, that's probably going to wrap it up. Let me just leave a bit of time for questions. So yeah, let me just go right to the end. So, well, in terms of the numerical experiments, currently what I'm working on is doing some MPI versions, so message passing interface versions of the method. That's what I'm quite excited about doing right now. So there's this package in Python. Normally, if you're doing MPI, that's a way to do parallel computing. You'd have to go through C, C++, but there is a nice package in Python that I'm finding a bit easier to use. So if you're familiar with it and you want to talk about it, then that'd be nice. But that's the main thing, because I want to see, if you do this method asynchronously in parallel, it's kind of an unknown how much benefit you get from that, and whether this is really worth doing things asynchronously or synchronously, or what sort of topology you should use, computational topology. We're sort of just scratching the surface there. And other things that we can do in the future is, we've figured out a way to put forward steps into the method. Actually, I don't think I've called it forward. I usually call it gradient steps, but sometimes we call gradient steps forward steps. It's usually used interchangeably. So we figured out how to put gradients into the method, but we don't know what else you can do with projective splitting. So it might be possible to do stochastic versions, higher order versions. We really have no idea how much you can sort of extend the method. We don't know how it performs on non-convex problems. So yeah, there's a lot of open problems to look into there. And there's some interest from other people in the operator splitting community. There's people studying inertial versions and some other variants as well. So there are some people studying the method out there. Okay, that'll probably wrap it up. So just, acknowledge Jonathan, and thanks for being here. And if you have any questions, go ahead.